In a previous episode, I finished configuring my outputs, improved 7-segment display, and used timer interrupts in order to make my while loop as clean as possible. However, there are some mistakes in our timer configuration. It's not like project is not working. If you followed my video and tried to create something yourself, it's probably working, but there are a few lines which are absolutely unnecessary and they do absolutely nothing in our case. And today I will briefly go through these mistakes and correct them, but focus of today's video is general purpose inputs. In my opinion, this video is going to be very boring. I'm going to use the most generic examples, but they're pretty necessary to understand what is happening here. Let's check the schematic really quick. As I said, the input driver is our main focus, actually this block. And today we will go through some things which are happening here, but let's go step by step. Once clock for port A is activated, we can go to pin configurations. We've been already working with push-pull output. We basically set mode bits to 1 and 0, which is combination of 2, and here we go, we have push-pull output. In order to configure pin as input, we have to leave mode bits as 0. The configuration bits have a few combinations here. Let's talk about first 3. The floating input is technically line here, nothing else is connected, none of these resistors are active, nothing. And if no signal is coming to this input, the Schmitt trigger is randomly turning on and off, setting this register bit as high or low, but it's happening completely randomly and actually can be influenced by probably a magnet. Technically it's very sensitive to noises. And in this configuration we have very unstable input. In order to stabilize our pin, we have to use resistor and connect it to either ground or power supply. The first configuration is when resistor is connected to ground. You see button connected to power supply and input, and then it goes to the ground through resistor. What does that basically mean? Well, when button is not pressed, we have input directly connected to the ground, which is basically just dragging input to low. But once we push the button, we close the circuit and current starts flowing from VDD to VSS. And once the current flows through the resistor, we have a voltage drop, which goes from 3 volts to 0 volts. And in the end of the day, we have 3 volts on the input, and input is going to detect high signal here. This resistor is called pull down resistor, and in this configuration, button is active high. The other configuration is when input pin is connected to a power supply via resistor. What that means that our input is constantly connected to high signal. But what happens once we press the button? Well, again we have a current flowing from the supply to ground, and again we have voltage drop on the resistor. And since our resistor is 10 kilo ohm and wires can be neglected, we get voltage drop from 3 volts to 0, and our input pin reads the 0 as a low signal. This resistor is now pull-up resistor, and the whole button configuration is active low. Sure, we can build these circuits on our breadboard, but I don't want to waste time and space on my breadboards for this bullshit, so we will just use what the microcontroller gives us. Actually, lucky us, we have input pull down and pull up resistors integrated in our microcontroller. Now, to activate these resistors, we have to configure register. Many bigger microcontrollers have specific register for pull down or pull up configurations. However, here it is a little bit confusing, at least it was for me, and the reason is that we actually have to configure ODR register, which is output data register. So I was not fully correct when I said that we will be working only on input drivers. Of course, here we have no relationship showed between output data register and input driver. And when I saw this for the first time, I was a little bit confused. Anyway, in order to set internal pull down or pull up resistor, we just have to set ODR register to 0 or 1. Now let's go to our circuit. As you can see, first 6 pins of port A are already used, they are tied to 7-segment display. So let's just use 2 pins we saved in the previous video. The pin 6 is going to be our input pin and pin 7 is going to be an indicator. This little jumper is not used right now, so don't pay attention to it. And now a very important part, we have to return to data sheets and check something out. Originally STM32 microcontrollers, at least many of them, are actually designed to work on 3.3 volts. Here's the table of pins. As you can see, there are much more ports and pins we actually don't have on our blue pill microcontroller. But we can see PB10 and 11, and if you check this carefully, you see this FT configuration, which means that they are 5 volt tolerant. However, PA6, which is going to be our input, is not 5 volt tolerant, and this means we should be very careful in order not to damage our microcontroller. In other words, we cannot use this usual power supply, which I connected here with this red wire, because it is connected to 5 volts. Instead of that, I have this brown wire, which is connected to 3.3 volts. Fine, we finished hardware part, now let's go to programming. So let's assume we already enabled clock for port A. let's go to configuration. Let's configure indicator pin first, which is going to be pin 7. To configure this pin as output, we have to set mode bits as 1 and 0 and leave configuration bits 0, 0. All in all, we have hexadecimal 2 here. For input mode, we have to set mode bits as 0, technically we are just leaving them as they are. And we will set configuration bits as 1 and 0, which stands for 8 in hexadecimal all in all here. As I said, to set these pins we have to make configuration of 2 and 8, which represents the indicator and input pin. And also we have to set our output data register, which is 16-bit register, and we are setting it as 40 in order to make pin 6 as low. And to test everything, I will write this condition in while loop, which will set LED as high if the button is pressed. Alright, let's turn on microcontroller. Don't pay attention, timer is still ticking. And it doesn't work, for some reason. The problem here is quite confusing actually. I had to spend some good time in order to understand what is happening. If you watched my first episode, you remember how I coded all this and initialized my 7-segment display. In this first line, I configured this register and enabled port A timer. However, I didn't do one very important thing after that. After enabling your port timer, you have to set configuration register to 0. In other case, if you try to reconfigure your port, it is not going to happen. And I think it's a good idea to move these 3 lines somewhere else. And for that purpose I created this function, which is already defined above. Now let's upload the code and see if it solved the problem. And here we go. The button is working, everything is just fine. Let's set the bool down for demonstration pretty quick. As I said, everything what you need is to set corresponding bit to 1. Let's rewire the circuit pretty quick and test it out. And yeah, here we go, we have active low configuration. Now let's do a step forward. And the leap forward is going to be, that's right, it's going to be interrupts. And actually it's not that scary as you would think. This picture is for alternative function input-output, but the same concept goes for GPIOs. As you can see, there are 16 lines from 0 to 15, which can trigger interrupts, and every single line is connected with pins of the same number from every single port. And we can enable any of these lines in order to trigger interrupts. And to enable interrupts, we have to make 3 steps. First of all, we have to configure interrupt mask register in order to enable our XT line. Then we have to decide what will trigger our interrupt, whether it is rising edge or falling edge. And then we have to configure interrupt handler for our line. And the lines are pretty interesting here. As you can see, first 5 lines are completely independent. But neither of those will satisfy our needs, because we are going to use pin 6. And the line 6 triggers the interrupt, which is handled by this one from 5 to 9. So as I said, we're just setting corresponding bits in interrupt mask register. And also I'll want my interrupt to happen at the moment when the button is pressed. Then we simply need to enable our handler and set its priority, and set corresponding bit in pending register. That's a weird move, but it is necessary in order to clear the bit in this register. The last thing is to configure our handler function. For now we will simply increment value in our 7-segment display and set pending register bit to 0. And we also don't want this timer to increment the value, so I will remove the line. And here it is, we increment the value by every button press. Actually, we can set our falling trigger as well. We can even set them together. And now our value will increment when we press and depress the button. Oh, the button is bouncing. Yep, the bouncing issue can be solved by software or hardware. By software, you just have to add a delay once the rising edge is detected. 50 milliseconds delay should be enough. Or we can simply add a capacitor. This should solve the problem as well. The last thing I want to do is to read analog signal. So let's see, what do I need for analog to digital converter. First of all, we need to enable ADC clock. For this we need to modify ADC bit in peripheral clock enabled register. Here it is. There are 2 ADCs, we will just use ADC 1. And the hexadecimal value is going to be 0200. Next is channel selection, and it could look a little bit confusing, but it's not that complicated. As you can see, we have 2 choices, it's regular group or injected group. I think it's important to understand what's the difference. The regular group can be started by external interrupt, by software, or it can run in continuous mode, which means it runs all over again every time the conversion ends. The injected group is smaller by itself, it can be started by external event or by software. And the most important difference between these two is that injected group has a priority over regular group. Anyway, we will use regular group and you will see why. So as we see, in order to start regular group, we have to configure sequence registers, which are right here. All in all, we have 3 sequence registers here, and the first one is a little bit different than the others two. It has a group of 4 bits which define the number of conversions which are going to be in the group. Let's say, for example, we want to make 3 conversions in a row, then we write 1 here and here. And then we have to go to the third sequence register where we will define the first 3 conversions. The others will be ignored. This is the first conversion, then second, the third, and they are going on and on until, I think, until 15 or what? No, up to 16. All in all, we can make 16 conversions in one group. For us, it will be enough just 1 conversion, so we will leave this as it is and we will not configure it anymore. But we will return to the third register and we will configure this group of 5 bits, and here we will write down the number of the channel which we are going to read. Now I just need to decide which pin I'm going to use for my analog input. And from this picture we can see that both pins 6 and 7 have analog input. I think the best idea to keep the button in place, it will be useful for us. Instead, we will remove indicator and replace it with potentiometer. I have a problem with my potentiometer here. It seems that it's not holding on the breadboard, so I will have to hold it manually. First of all, let's enable clock for ADC and configure our sequence. And of course we have to set pin 7 as analog input, which is actually 0. Next move, and for now the last, is choosing the conversion mode. And the simplest one is actually single conversion mode. For this mode we just need to modify this configuration register and set this ADC on bit to 1. Let's do it here pretty quick and let's see what happens. Oh, I absolutely forgot, we actually have to take the data out, and for this we have to access ADC data register. This is a 12-bit register which can contain value up to 4095, and we will extract this value into our 7-segment display. And for some reason display doesn't show anything. Well, the problem is that we didn't read datasheet carefully enough, and there is something hiding behind this bit. And what is hidden here is quite difficult to notice, but actually, once we set this bit once, we enable ADC, and once we set it to 1 again, we start a conversion. In other words, we have to set this bit to 1 again in order to get some kind of information. So let's try to solve the issue by enabling this bit again, and I will do this in the external interrupt handler. So technically, once I push the button, I should be able to get some data into my display. And as you can see, it works. Let's try to change the value of potentiometer. Boom, it changed. It's only you saw that delay is because the timer is set to 1 second, so we are changing data of the display every second. And I think it's a good time to return to timers where, as I said, I did some mistakes. So let's try to figure them out. Well, first of all, my timer 3 is responsible for updating my display. Timer 2 is doing all the display thing, but timer 3 is managing data. So I think if I leave 100 milliseconds, it should be pretty good. And also, the mistake I did here was actually putting this event generation line, which actually is useless, because event doesn't have to do anything with interrupts. It's important to understand that interrupt and event are 2 absolutely different concepts. The event causes microcontroller to do something behind the code without interference. The interrupt stops the main code and forces microcontroller to execute some kind of piece of code we put into handler. So we can technically remove this line, which is not necessary at all. Now, turning off the timer and resetting it is important when we actually want to reconfigure our timer. Once we initialize it for the first time, these moves are, I think, not necessary here. So you are free to experiment here. I will leave it as they are, but I believe it's not necessary. Alright, I think I've figured the problem out here, and our timer should respond much faster. We shouldn't see such delays when I press the button. Now, the last thing I want to do is to make my ADC to work continuously. I don't want to press the button every time I want to see a conversion. And for this, we actually have the mode, which is called continuous. And this is pretty much the reason why I chose regular conversion group. One more difference between the injected and regular groups is that regular group can start itself once the loop is done. I mean, once all channels described in sequence register are converted, the regular group starts itself again. And this can be pretty easily achieved by modifying second configuration register. We just need to set the second bit to 1. The only thing I will still want to modify is probably remove the button completely. It's not needed for us anymore. So I'll just leave this interrupt handler empty. And here I have fully working ADC. Of course, this example is totally generic and boring, but everything depends on how you will use it. You can control some kind of device, for example the servo motor, or you can just make a colorful decoration. Quite useless, but for somebody it will look like a miracle. And this is actually a PWM controlled LED, which I am going to explain in the next video, since this is another topic where, again, we are returning to GPIO. No, this is not GPIO. This is already alternative function. We are going to go to alternative function and learn something a little bit more complicated here. Of course, you're free to try yourself. Maybe you will find a better solution than me. Anyway, this is it for today. I hope you enjoyed the video. Please hit the like button and make sure to subscribe. That was me, David Ovi, and I will see you in the next video, whatever it is going to be, and whenever.